Welcome to this presentation. In this model, we'll be looking at the mobile transport layer, which consists of TCP congestion control, fast transmit and fast recovery, indirect TCP, snooping TCP, mobile TCP, timeout freezing, selective retransmission, and transaction-oriented TCP. The TCP, that is Transmission Control Protocol, provides a connection-oriented, reliable, and byte-stream service. The term connection-oriented means that two applications using TCP must establish a TCP connection with each other before they can exchange data. So, traditional TCP, which guarantees in order and reliable delivery, is the classical wired networks transmission protocol. And a transport layer protocol such as TCP has been designed for fixed network with fixed end systems. And data transmission takes place using network adapters, fiber optics, copper wires, and special hardware for routers. And congestion may appear from time to time even in a carefully designed networks. The probable reason for packet loss in a fixed network is a temporary overload some point in a transmission path, that is state of congestion at a node. And the packet buffers of a router are filled and the router cannot forward the packets fast enough because the sum of input rates of packets destined for one output link is higher than the capacity of the output link. Okay, and the only thing a router can do in this situation is to drop packets. A dropped packet is lost for the transmission and the receiver notices a gap in the packet stream. And now the receiver doesn't directly tell the sender which packet is missing, but continues to acknowledge all in sequence packets up to the missing one. Now the sender notices the missing acknowledgement for the lost packets and it assumes that a packet is lost due to congestion. So retransmitting the missing packet and continuing at full sending rate would be now unwise because this might only increase the congestion. And the slow start is nothing but TCP's reaction to a missing acknowledgement is quite severe, but it is necessary to get clear of this congestion quickly. So the behavior TCP shows after the detection of congestion is called slow start. Okay, and the sender now it always calculates a congestion window for a receiver. The start size of the congestion window is one segment usually, and the sender sends one packet and it waits for the acknowledgement. And if this acknowledgement arrives and the sender now increases the congestion window by 1, now sending 2 packets. And this scheme doubles the congestion window every time the acknowledgements come back, and which takes one round trip time. And this is called exponential growth of the congestion window in the slow start mechanism. So, but doubling the congestion window is too dangerous. The exponential growth stops at the congestion threshold to avoid this dangerous situation. As soon as the congestion window reaches the congestion threshold, further increase of the transmission rate is only linear by adding 1 to the congestion window each time the acknowledgements come back. Right. The two things led to a reduction of the congestion threshold. One is the sender receiving continuous acknowledgement from the same packet, and this informs the sender that the receiver got all packets up to the acknowledged packet in sequence. So in a TCP, receiver now sends acknowledgements only if it receives any packets from the sender. And receiving acknowledgement from a receiver also shows that the receiver continuously receives something from the sender. The gap in the packet stream is not due to severe congestion, but a simple packet loss due to a transmission error. And the sender now can retransmit the missing packets before the timer expires. And this behavior is called fast retransmit, right? And the receipt of acknowledgements shows that there is no congestion to justify a slow start, and the sender can continue with the current congestion window. And the sender performs a fast recovery from the packet loss, and this mechanism can improve the efficiency of the TCP dramatically. While slow start is one of the most powerful mechanisms in fixed networks, it severely decreases the efficiency of the TCP if used together with the mobile receivers or senders. And the reason for this is the use of slow start under the wrong assumptions. For a missing acknowledgement, TCP concludes a congestion situation. While this may also happen in networks with mobile and wireless end systems, it is not the main reason for the packet loss. So mobility itself can cause packet loss, And there are many situations where a soft handover from one access point to another is not possible for a mobile line system. For example, when using a mobile IP, there could be still some pockets in the transit to the old foreign agent while the mobile node moves to the new foreign agent. So the old foreign agent may not be able to forward those pockets to the new foreign agent, or even buffer the packets if disconnection of the mobile node takes too long. And this packet loss has nothing to do with the wireless access, but it is caused by the problems of rerouting the traffic. So the TCP mechanism detecting missing acknowledgements via timeout and concluding packet loss due to congestion cannot distinguish between the different causes. And this is a fundamental design problem in TCP. Now let us see the classical TCP improvements. The adaptation of TCP to congestion control causes a lot of problems in wireless domain. The wireless domain has packet loss, high packet loss and variable latency, which may cause the TCP to respond with slow start. So several alternatives have been proposed to alter the existing TCP protocol to suit the wireless domain. And the simplest idea would be to design a new TCP protocol for the wireless domain. And in the first case, let us see about the indirect TCP. And two challenging approaches led to the development of indirect TCP. One is that TCP performs poorly together with wireless links. And the other is that the TCP within a fixed network cannot be changed. So ITCP segments TCP connection into a fixed part and a wireless part. Right. And this diagram, as you can see, it shows the example of a mobile host connected with a wireless link and an access point to the wired internet. The corresponding node could also use the wireless access. The standardized TCP is used between the fixed computer and the access point, as you can see. Now, computer in the internet recognizes any changes to this TCP. Instead of mobile host, the access point now terminates the standard TCP connection, acting as proxy. This means that the access point is now seen as the mobile host for the fixed host and as the fixed host for the mobile host. So between the access point and the mobile host, special TCP is adapted to wireless link will be used in this case. Right. The foreign agent now controls the mobility of the mobile host anyway, but it can also hand over the connection to the next foreign agent when the mobile host moves on. And the corresponding host in the fixed network doesn't notice the wireless link or the segmentation of the connection. And the foreign agent now acts as a proxy and relays all data in both directions. If the correspondent host sends a packet and the foreign agent acknowledges this packet and tries to forward the packet to the mobile host, and if the mobile host receives the packet, it acknowledges the packet, and however this acknowledgement is only used by the foreign agent. So if a packet is lost on the wireless link due to transmission error, the correspondent host would not notice this. So in this case, the foreign agent tries to retransmit this packet locally to maintain a reliable transport. Here are some of the advantages of ITCP. It doesn't require any changes in TCP protocol, and transmission errors, that is lost packets, cannot be spread into fixed network. And partitioning into two connections also allows the use of different transport layer. And the main disadvantages is the loss of end-to-end semantics of TCP might cause problems if the foreign agent partitioning the TCP connection crashes. And in practical use, the increased handover latency may be much more problematic. And the next classical TCP improvement is snooping TCP. One of the drawbacks of ITCP is the segmentation of the single TCP connection into two TCP connections. So this loses the original end-to-end TCP semantic. So now the snooping TCP works completely transparently and leaves the TCP end-to-end connection unbroken. This is the main advantage of snooping TCP. And the main function of the enhancement is to buffer data close to the mobile host to perform fast local retransmission in case of packet loss. A good place for the enhancement of TCP could be the foreign agent in the mobile IP context. You can see in this figure. In this approach, the foreign agent buffers all packets with the destination mobile host and additionally snoops the packet flow in both directions to recognize the acknowledgements. The reason for buffering packets towards the mobile node is to enable the foreign agent to perform a local retransmission in case of packet loss on the wireless link. The foreign agent buffers every packet until it receives the acknowledgement from the mobile host. So if the foreign agent doesn't receive an acknowledgement from the mobile host within a certain amount of time, then either the packet or the acknowledgement had been lost. So alternatively, the foreign agent could receive a duplicate acknowledgement which also shows the loss of packet. Now, the foreign agent retransmits the packet directly from the buffer, performing a much faster retransmission compared to the correspondent host. And the timeout of acknowledgements can be much shorter because it reflects only the delay of one hop plus the processing time, right? And the data transfer from the mobile host with the destination correspondent host will work like the foreign agent snoops the packet stream, snoops into packet stream to detect gaps into the sequence of TCP. As soon as the foreign agent detects a missing packet, it returns a negative acknowledgement to the mobile host. And the mobile host can now retransmit the missing packet immediately. And reordering of packets is done automatically at the host, at the correspondent host by TCP. And the advantages of snooping TCP are here the end-to-end TCP semantic is preserved, and the correspondent host doesn't need to be changed, and it doesn't need a handover of state. And the disadvantages are using negative acknowledgement between foreign agent and the mobile host assumes additional mechanisms on the mobile host. And all efforts for snooping and buffering data may be useless if certain encryption schemes are applied end-to-end between the correspondent host and mobile host. And the next classical TCP improvement is mobile TCP, that is our MTCP. This approach has the same goal as ITCP and snooping TCP. Actually, MTCP wants to improve the overall throughput, to lower the delay, to maintain the end-to-end semantics of TCP, and to provide an efficient handover. Additionally, it is especially adapted to the problems arising from lengthy or frequent disconnections. And this mobile TCP splits the TCP connection into two parts as ITCP does, right? And an unmodified TCP is used on the standard host, or that is supervisory host connection, while an optimized TCP will be used on SHMS, that is supervisory host mobile host connection. The supervisory host is responsible for exchanging data between both the parts, similar to the proxy in ITCP. And this mobile TCP approach assumes a relatively low error bit on the wireless link. Therefore, it doesn't perform caching or retransmission of data via the SH. Okay, and the SH monitors all packets into the MH and acknowledgements return to the MH. And it assumes that that is, if the SH doesn't receive an acknowledgement for some time, it assumes that MH is disconnected. And if it then chokes the sender by setting the sender window size to 0. Setting the window size to 0 forces the sender to go into the persistent mode. That is, the state of the sender will not change no matter how long the receiver is disconnected. So this means that the sender will not try to retransmit data. As soon as the SH detects the connectivity again, it reopens the window of the sender to old value. And the sender now can continue sending at full speed. This mechanism doesn't require the changes to the sender TCP. The wireless side uses an adapted TCP that can recover from packet loss much faster. And this modified TCP doesn't use slow start, and thus the MTCP needs a bandwidth manager to implement fast sharing of over the wireless link. And next we'll see about timeout freezing. Well, the approaches presented so far can handle short interruption of the connection, either due to handover or transmission errors on the wireless link. Some were designed for longer interruptions of transmissions. Examples of the use of mobile host in a car driving into a tunnel, which loses its connection to a satellite. For example, however, many tunnels and subways provide connectivity via a mobile phone or a user moving into a cell with no capacity left over. In this case, the mobile phone system will interrupt the connection. And the reaction of TCP even with the enhancement of above, would be a disconnection after a timeout. Quite often, the MAC layer has already noticed connection problems before the connection is actually interrupted from a TCP point of view. And additionally, the MAC layer knows the real reason for the interruption and doesn't assume congestion as TCP would. And the MAC layer now can inform the TCP layer of an upcoming loss of connection or that the current interruption is not caused by congestion. And the TCP can stop sending and freezes the current state of its congestion window and further timers. And if the MAC layer notices the upcoming interruption early enough, both the mobile and corresponding host can be informed. With the fast interruption of the wireless link, additional mechanism in the access point are needed to inform the correspondent host of the reason for interruption. Otherwise, the correspondent host goes into slow start, assuming congestion, and finally breaks the connection as soon as the MAC layer detects connectivity. And the advantages of timeout freezing is the scheme is independent of data, and it offers a way to resume TCP connections, and all mechanisms rely on the capability of MAC layer to detect future interruptions. So these schemes need a resynchronization after interruption. And the main disadvantage here is the lot of changes have to be made in software for MH, CH and FE. Thank you.